So let's begin this video with an example. We have the polynomial x squared plus 1. That's a polynomial with coefficients in z3 that has no roots in z3. You could plug in 0, 1, and 2 for x and show that you never get out 0 mod 3. So the thinking is I'd like to find a root in some field that contains z3. So I want to enlarge z3 to a bigger field, and that field should contain a root of x squared plus 1. So the thinking is take a new field E to be the ring of polynomials with coefficients in z3 mod the polynomial x squared plus 1. Now this is indeed a field because x squared plus 1 is irreducible in z3. It has no roots in z3 and it's degree 2, so it's irreducible. Therefore, the ideal generated by this polynomial is maximal, and thus the quotient ring is a field. So there's two things I'd like to notice about this field E. Number one is if I define a function phi that goes from z3 to my enlarged field E by sending an element A in my ring z3 to the coset A plus my ideal, then this function phi is a ring homomorphism. You could check that. And it's also one-to-one. We're going to check that in a minute, but take it for granted for now that phi is indeed a one-to-one ring homomorphism. What that says is that Z3 is isomorphic to a subfield of E. So you could think of E as containing a copy of Z3. So it really is an enlargement of Z3. And second, I claim that there's an element in E that is a root of this polynomial. Here's what it is. I'm going to take alpha to be the element x plus my ideal. That's an element in my factor ring. If I calculate alpha squared plus 1, that's plugging an alpha into my polynomial, I get the coset x plus the ideal squared plus 1. Now I wrote down 1 here. 1 is the multiplicative identity in the field. The multiplicative identity in this field is the coset 1 plus x squared plus 1. Now the way that you multiply two cosets together is by multiplying their representatives, and the way that you add two cosets together is by adding their representatives. So this is really the coset x squared plus 1 plus my ideal. This is the 0 in the field. This is 0, plus my coset. That's the additive identity, meaning that alpha is indeed a root of the polynomial x squared plus 1. So this example is a motivating example for the general theorem. This kind of idea will always work. You take a polynomial in your ring of polynomials over some field, you could always enlarge your field to another field that contains a root. So let's write down the general statement and prove it. This is a nice theorem. So theorem. This one is called the fundamental theorem of field theory. So here's the statement. take a polynomial, p of x, in your ring of polynomials over some field to be irreducible of degree bigger than or equal to 2. I didn't really care to take a polynomial of degree 1 because every polynomial of degree 1 will have a root. And I took it to be irreducible because if I have a polynomial that does not have a root in my field, I could always break it into irreducibles that don't have roots in that field as well. So without loss of generality, I'm going to take p to be irreducible of degree 2. And then there is a field E such that two things hold. Number one, F is isomorphic to a subfield of E, and 2, E contains a root of p of x, just like what we did in our example. Okay, so the proof is outlined by our example. We're going to follow the same process. I'm going to take my field E to be the ring of polynomials over F, but I'm going to mod out by this irreducible polynomial. Again, this is a field. P of x is irreducible, so the ideal is maximal. The quotient ring is indeed a field. So then, property 1, define a ring homomorphism phi that sends your field to this larger field E by sending an element A in your field to A mod this ideal generated by the irreducible polynomial P. Now I claim that this is a one-to-one ring homomorphism. So to show one-to-one, I'm going to assume that phi of A equals phi of B. Hopefully I'll conclude that A does indeed have to equal B. So this means, if these two cosets are the same, then that means that A minus B plus my ideal has to equal 0, which is just the ideal itself. Now what this means is, therefore, A minus B has to be in the ideal generated by P of x. Now the degree of this polynomial is degree 1 or 0 even. So A and B are in your field F. There's no x, this is just a degree 0 polynomial. There's no x involved. So since P of x has degree bigger than or equal to 2, so since the degree of the polynomial, I guess you can call it, is just an element in the field, A minus B is less than the degree of P of x, this implies A minus B has to be 0. The ring, or the ring of polynomials over some field, is a principal ideal domain. that means every ideal is generated by a polynomial with minimum degree in that ideal. So if p of x generates an ideal, then p of x is the polynomial of smallest degree in that ideal. So if you have any other polynomial of smaller degree, then it's got to just be 0. So a equals b. I've actually shown using this argument here, this is a parenthetical because it's not needed in the proof, but it's good to realize that this shows, for example, that the field E can be expressed as polynomials r of x plus my ideal such that the degree of my polynomial r of x is less than that of p of x. But anyway, I've shown that a equals b. Therefore, I've shown my function is 1-to-1. And I'm not going to verify it's a ring homomorphism. It splits over addition and multiplication, but that's a routine verification. So I claim that I'm shown that phi is a 1-to-1 ring homomorphism. Therefore, F is isomorphic to a subfield of E. So that verifies condition 1. So let's look at condition 2. Condition 2, I need to find a root of my polynomial. And I'm going to do the same thing I did in my example, and I'm going to take alpha to be x plus my coset, my ideal. Then, what is p of alpha? So p of alpha, that would be the same as plugging x plus this ideal into my polynomial. Now, in the same way that we saw up here, the way that you multiply two cosets together is by multiplying their representatives. The way you add two cosets together is by adding their representatives. So if you do any polynomial involving cosets, then the result will be just this. So p of alpha will be p of x plus the coset, the ideal generated by p. All right, there. That's the end of the proof, because this is the 0 in the field. So this is the 0 element, the additive identity in E. So there, I've done it. I found a field E that's containing f and also a root of my polynomial. All right, we'll do an example of this in the next video. I'll see you there.